Okay, everyone, let's start then. Let's begin. So we have done forces. We are done with most of the concepts that we need to know about in forces and equilibrium. We've talked about what a force is. It's a vector quantity that has both magnitude and direction. Its unit is Newton. We talked about how to describe direction of a force. Then we talked about resolving forces and finding resultant force. Right? We're done with all of these concepts. We did some examples on that. We talked about equilibrium. When we have equilibrium and the resultant of all the forces acting on an object is zero, the object is said to be in equilibrium. And in that case, we said we would just be equating the opposite forces. The forces acting towards the left side, we would equate them to the forces acting towards the right side, and the upward forces will be equal to the downward forces, right? That's what we do when we have equilibrium. We did some examples of that. And then we talked about the concept of we talked about the different forces that you sometimes have to represent yourself. They're not explicitly stated in the question sometimes. First of all, we talked about weight. Weight is defined as mass into gravitational acceleration. W equals m into g. It always acts vertically downwards. Then we talked about normal reaction force. Normal reaction force is a force applied by a surface on an object that applies perpendicular to the surface. We talked about this and different examples of how the reaction force could work in different situations. We also talked about the concept of tension. Tension is a force applied by a string on an object. It always acts away from the point of reference. It acts towards the string and away from that object. And we considered the different cases that we have for tension, that when do we have equal tensions, when multiple strings are involved, or two different parts of the same string are involved, when do we have the same tension on both sides. We talked about this concept as well, right? So equal tensions are when there's a single string and that string is free to slide through the object. In that case, you have equal tension on both sides. When any of those two conditions is not met, that means whether either it's not a single string, or maybe if it's a single string, it's not free to slide. In that case, you do not assume equal tensions. Now, the two most common cases that you get for equal tensions are when you have a string that's passing through a ring like this. In that case, you have equal tension on both sides, because through a ring, a string is free to slide, free to move. And the other common case is when you have a string passing over a pulley. That's another common case. In this case as well, the tension on both sides is equal. Apart from this, most of the cases that you get, in that case, the string is not free to slide. In that case, the tension is going to be different on both sides of the string. Okay, that's what we did. And again, we did some examples. And in the last class, we'd also talked about this theorem called Lamy's theorem that makes our working much simpler in some types of questions where you have three forces and those three forces are in equilibrium. When you have a situation like this, when you have three forces and the forces are in equilibrium, in that case, you can use this Lamy's theorem, and that makes your calculation much quicker in that case. Okay, that's what we did. So by now, I expect you to have completed and submitted the forces and equilibrium worksheet, the first one that I posted. Now we are deciding, now we are starting our next concept, which is the last one that we have in this topic, but the one that's more complicated than the other concepts that we've done until now. And it's the last kind of force that you have to represent yourself in questions. And that's friction. That will not explicitly be given in many cases. You'll have to make sure that you do represent it on your diagrams as well. So earlier we've talked about weight and normal reaction and also tension. This is the fourth force that we're talking about now, and that's called friction. Okay, now let's talk about friction then. Let's say we have a surface. Let's try to understand it using an example. Let's say we have a surface. And on the surface, there is a block placed. Okay, so we have a surface and there's a block placed on top of the surface like this. And what you're doing is we're applying a force on this block towards the right side or maybe towards the left side. Let's say you're applying a force of 1 Newton to the right side. Now let's assume this block has a weight of 500 Newton. So we are accustomed to thinking of this in kilograms. So 500 Newton is approximately equal to 50 kilograms. Okay, so you can think of something that has a mass of 50 kilograms placed on a surface. And what you're doing is you're applying a force towards the right side of 1 Newton. That's an equivalent of 0.1 kg. Now, what do you expect? Is this block likely to move? What do you think? Any ideas? Do you think this block is going to move because of this? It's very unlikely, right? Because it's a 500, the weight is 500 Newton. You're just applying a force of 1 Newton on the right side. Practically speaking, if you had a block of 50 kg placed somewhere, and you were to push it by just applying a force that's equivalent to 0.1 kg, it's very unlikely that it's going to move. But if you look at the forces applying on this block, there's a 1 Newton force applying on the right side, and there would be a reaction of force that would be applying upwards. In this case, that will also be 500 Newton. Upwards and downward forces are balanced because the weight was 500. In this case, the reaction would also be 500 if there's no other vertical force. You're applying a force of 1 Newton. Looking at this diagram, there should be a resultant force of 1 Newton acting towards the right side, and the block should start moving. But as most of you are saying, it most likely is not going to move. Why is that? Because there's some friction between these two surfaces. There's some friction between the block and the surface. That is making the object stay in its position. Where is that friction going to apply? We're applying a force of 1 Newton to the right side. The friction between the surface and the block is going to stop that by applying an equal force on the left side of 1 Newton. So there'll be a force of 1 Newton acting towards the left side in this case that will stop the block from moving. It will stay in equilibrium. You have 1 Newton applying on the right side, 1 Newton applying on the left side by the surface. That keeps the object in its equilibrium position and does not let it move. So this force that resists motion, that stops an object from moving, this force is called friction. Okay, now let me write that down. What is friction? Friction is the force applied by a surface on an object that opposes the motion of the object. And in this case, it's not really moving as such, so we can say it opposes the possible motion. It opposes the possible motion of the object. Possible motion of the object. Okay, it opposes the motion of an object. Now, what's the direction of friction? We talked about the direction of weight earlier, direction of resultant earlier, the direction of tension earlier, right? What about friction? Against motion, yes. But along with that, there's another thing that you need to remember. Friction always acts one opposite to motion, yes. It's also parallel to the surface that you have. It always acts parallel to the surface. So remember, there was another force applied by a surface on an object as well. That was called the reaction force. That was also a force that a surface was applying on the object. but that was acting perpendicular to the surface. So there are two types of forces that a surface applies on an object. One is normal reaction that acts perpendicular, and the other is friction that acts parallel to the surface. And these two forces combined are actually called contact forces. So you will see this terminology being used sometimes as well. Contact force is basically a force that applies because of contact between two objects, between two surfaces. There are two types of contact forces. One we have done before, and that was normal reaction. Normal reaction used to act perpendicular to the surface. Right? That was the direction of normal reaction. What about friction? Friction acts parallel to the surface. Friction acts parallel to the surface. What am I writing? Parallel to the surface. Okay. These are two types of contact forces: friction and normal reaction. So that's what the concept of friction is. Now, let's consider the same example again. We have a weight of 500 Newton, and what's happening is we are applying a force towards the right side that has a magnitude of 1 Newton. And most of you are saying it should not move by that tiny amount of force. Now, let me just get rid of reaction force from there. Of course, it exists, but I'm just reducing the clutter a bit. Okay, so we're saying 1 Newton force on the right side. You'll have friction acting on the left side of 1 Newton as well, and that will counter this force. Okay. What if you had a force applying on the right side of 5 Newton? What do you think is going to happen to the friction? What would be the value of friction be in this case? 5 Newton applying on the right side, the friction would also match that, right? The friction would also match that 5 Newton. And the friction on the left side would also become 5 Newton in this case, and the object will stay in equilibrium. Okay, the object will stay in equilibrium. So friction is not going to remain constant. Okay, it depends on the amount of force that you are applying. If you are applying 1 Newton, friction counters that 1 Newton, and it's also equal to 1 Newton. If you are applying 5 Newton, friction is also 5 Newton. It counters that 5 Newton force that we're applying on the right side. If you were to apply a force of, let's say, 1000 Newton, what do you think? Is the object going to move now? It was not moving at 1 Newton. It was not moving at 5 Newton. What if I was to increase this force to the right side to 1000 Newton now? What do you think is possible now? Is it possible that the object is going to move? It's much more likely, right? It's much more likely. So now most of you would say, if not at 1000, 10,000. If I were applying a force of 10,000 Newton to the right side, it's almost certain that this is going to move now. Okay. So basically what happens is between 5 Newton and 10,000 Newton, there comes a point somewhere where the object does start to move. So at 1 Newton, it was not moving. At 5 Newton, again, most of you think it would not move. But then at 10,000 Newton, it is most likely going to move. Now, how is that happening? 5 Newton was being countered by friction, but if it starts moving at 10,000, if it does start moving when you apply a force of 10,000 Newton, that means the friction that you had between the surface and the object, this is not able to counter the 10,000 Newton anymore, because now it's too much. Okay, the 10,000 Newton force that you're applying, that's a bit too much for the friction to be able to counter. So now the object starts moving. So the idea is that friction is not infinite. It has some limit. It has some maximum value. So there is going to be some maximum value of this friction. Okay, this friction is going to have some maximum value. Now, how do you find that maximum value? We will talk about that in a few minutes. Let's suppose this maximum value was 50 Newton. Let's suppose the maximum value of friction, or we use a different number because we have 500, might get confused. Let's say 40 Newton. Let's say the maximum value of friction in this particular case was 40 Newton. Okay. Now, what does that mean? If the maximum value of friction was 40 Newton, then if you were to apply a force of 5 Newton, the friction would also become 5 Newton. If you were to apply a force of 15 Newton, the friction would also become 15 Newton and the object will still not move. If you were to apply a force of 40 Newton, the friction would also become 40 Newton and the object will still not move because it can exert a friction of 40 Newton, right? So 40 Newton can be counted. But now if you were to increase the force even slightly more than 40, increase the force to even slightly more than 40, what happens then? The object starts moving. For example, if you were to apply a force of 60 Newton, what would be the value of friction in this case? The maximum friction that the object can apply, that the surface can apply, is actually 40 Newton. So friction in this case is still going to be 40 Newton. That cannot go above 40 Newton. And now the object does start moving with the resultant force of 20 Newton on the right side. Because the friction cannot counter this force that you're applying on the right side anymore. The maximum friction in this case was just 40 Newton. Okay. So what we understand from this discussion is that there is going to be some maximum value of friction beyond which the object is going to start moving. If you were to apply a force beyond that threshold, then the object is going to start moving because friction would no longer be able to counter that force that you're applying. Okay. Now, the next question is, okay, we have a maximum value of friction, but how do we get to that maximum value? Where do we get that maximum value from? This maximum value depends on two things. So friction, why do we have friction between surfaces? Because there's some roughness between the surfaces, right? There's some roughness. The surface might be rough. The object surface might have some roughness. Because of that, this friction exists. So this maximum value of friction, it actually depends on two things. Number one, it depends on something that we call mu. This means coefficient of friction. And the second thing it depends on is R, which is the normal reaction. The normal reaction force that the surface is applying on the object. These are the two things that on which the maximum value of the friction depends. Okay. Now let's try to understand why that is the case. This is how you would find the maximum value of friction, but why these two things? Now, mu is kind of obvious because mu actually represents, this value of mu is actually something that quantifies the roughness of the surface. So for instance, if you have, if the surface here was ice, then the friction would be less as compared to if the surface was grass or maybe if it was wood. So depending on the kind of surface that you have, the friction would be less or more depending on how rough the surface is. So ice is relatively smooth. Wood would be rough. Grass would probably be more rough. So as the roughness of the surface increases, the friction is supposed to increase. Okay. But how do we quantify this roughness? Mu is basically the quantification of that roughness. Mu is high if the surface is more rough, mu is less if the surface is less rough. So mu for ice would be less, right? And mu for grass may be more, mu for wood may be more. So mu is basically quantification of the roughness of the surfaces. So you can say this is a number. This is a number that quantifies. It's a number that quantifies roughness between surfaces. Okay, so for every set of surfaces and objects, you would have a different coefficient of friction, and that basically is a number that quantifies roughness. Okay, so that's kind of understandable that the more rough a surface is, the more friction there is going to be. Okay, now generally speaking, the values of mu are actually between 0 to 3 or 4. So these are small values. If it's close to 0, the surface is less rough. If it's away from 0, the surface is more rough. So this is what I took from a book. These are some common values of friction that you have for different kinds of surfaces. If you have, for instance, wood sliding on wood, mu is generally between 0.2 and 0.6. If you have sandpaper on sandpaper, that's very rough. That will be 2.0. As compared to, for instance, skis on snow, that they would have less roughness, less friction. This is only 0.02. So if the mu value is small, that means this roughness is less. If mu value is greater, it's away from 0, then there's more roughness. But you can see most of the values are actually between 0 and 2. In fact, all of the values are between 0 and 2. Sometimes it's greater than 2 as well, but it doesn't go much higher than 3, 4 generally. Okay, the closer it's to 0, the less rough it is. Now, you don't have to remember these values. This is just a practical understanding of how these mu values generally vary, as in what range the mu values generally are. You will generally be given this value in the question, or if you have to find it, you would have the other things given. For example, you might have R given, or you can find R somehow, and you can find F max somehow, and then using those values, you can find the value of mu. Okay. In practice, it's found using experiments, but you would either be given this value in the question, or you may be able to find that value using R and F max. If the other two things are given, you can find mu like this: F max over mu. Okay, so F max over R. You can find mu like that. So that's where mu comes from. It quantifies the roughness of the object, roughness of the two surfaces, in fact, the surface and this the object, both of them. It quantifies their roughness together. So if mu is higher, F max is also going to be higher. The other thing that this maximum value of friction depends on is reaction. Now, how does that make sense? Why does it depend on reaction? Let's try to understand that as well. Let's consider the surface. And let's say on the surface, we have that same block that has a weight of 500 Newton. Okay. And let's say we have another surface, in fact, the same surface and a similar block that has the same roughness as the first one. We have another block placed here. They're both made from the same material. Let's call this block B. The material that this block is made from, the outer surface is made from, is the same. But the weight of this block is, let's say, just 5 Newton. Now, keeping everything else the same, basically considering that the roughness of both these surfaces is exactly the same. A and B, both are the same in terms of the surfaces. Only the weights are different. Which one do you think is going to have more friction, A or B? Is A going to have more friction or B going to have more friction? A, right? Because A has more weight. Now, why having more weight results in more friction? Because if A has more weight, what that means is A is applying a force of 500 Newton on the surface. So that basically quantifies the strength of the contact between the block and the surface. So they are connected by a force of 500 Newton. The object is applying a force of 500 Newton on the surface. The surface is applying a reaction force of 500 Newton. So they are strongly connected like this. Similarly, on the other hand, if you look at this block B, the force that they are applying on each other is only 5 Newton. So the block that has more weight, that is likely to have more friction. Okay, that's likely to have more friction as compared to the other one. So it looks like the friction value should depend on weight, but that's not what we have in the formula here. In the formula, we have reaction, not weight. Now, how does that make sense? Well, think about it. What if we had an upwards force applying like this on this first surface? Let's say we were trying to pull this block up by a force of, let's say, 480 Newton. And let's say the weight of the second block was actually 50 Newton. Now, the weight of the first one is 500 Newton. The weight of the second one is 50 Newton. If you look at the second box, the reaction force is going to be 50 Newton as well, because there's no other vertical force. So if we have equilibrium, if the downward force is equal to the upward force is also going to be 50. Reaction is supposed to be 50. In the first case, what is the reaction value going to be? If the downward force is 500 Newton, if the downward force is 500 Newton and you're applying a force of 480 Newton upwards, the remaining force is only going to be 20 Newton. So the reaction value here is only going to be 20 Newton. Now, in this case, if you think about the first block, what is the strength of contact of this block A with the surface? Yes, it has a weight of 500 Newton, but the problem is you're also applying a force of 480 Newton upwards. So 480 out of that 500 is actually neutralized. It's countered by this 480 Newton force. So the resultant force that's actually applying on the surface is only 20 Newton. And the surface is giving a reaction of that 20 Newton here. So the strength of this contact is no longer 500 Newton. The strength of this contact is actually only 20 Newton now, because you're applying a force of 480 Newton upwards. The net force that the object is applying downwards is only 20 Newton now. And the surface is just giving a reaction of that 20 Newton here. In the second case, if you have no other force, this is 50. Reaction is also 50. So the net force that the object and surface are applying on each other is 50 Newton. So in this case, the strength of contact between the block and the surface is more in case of B as compared to A. B is connected to the surface by a force of 50 Newton. A is only connected to the surface by a force of 20 Newton. What force captures this strength? It's not the weight. It's actually the reaction force that captures the strength of this contact. So the block A had a reaction force of 20 Newton acting towards it. So that is connected by a force of 20 Newton to the surface, and object B is connected by a force of 50 Newton to the surface. So the higher the reaction is going to be, the higher is going to be the friction. So if reaction is higher, friction is also going to be higher. That is why the second thing that the friction depends on is reaction. It's not the weight, it's reaction. Okay, so that's why we have R here instead of weight. So now what we understand is we have a maximum value of friction that is given by mu into R. Okay, that's what the maximum value of friction is. So this is what you need to remember now. For any two surfaces, you will have some maximum value of friction. How can you find that maximum value? By using this formula, F max equals mu r. F max means the maximum possible friction, Mu stands for coefficient of friction, and R stands for normal reaction. Okay, so that's what this relationship looks like between F max, mu, and R. Is this all right to everyone? Any questions on this? Any problems?
No, sir.
No? Okay, so that's what the maximum value of friction is. Now, let's get back to that same example again. We had these different possible forces acting. Now, you saw that the friction value was not always equal to the maximum value. If the maximum value was 40, if F max was equal to 40 Newton, it does not mean that the friction would also always be 40. It depends on what force you're applying. So in one case, it was 1 Newton. In another case, it was 15 Newton. And then it was 40 Newton. And it was 40 Newton here as well. So it can keep changing. And the maximum possible value would be this value that we have here. Now, let's get back to these. Let's consider these scenarios again. And see how the friction is related to the maximum value in each of these different cases. And what are these different cases called? Let me just get rid of this situation. Just consider the other three. Okay. So we have these different possibilities. In the first case, the one that I have at the bottom here, we have a force applying towards the right side of 15 Newton. And the friction, the maximum value of which was 40 Newton. Since the force that we're applying is 15 Newton, that's less than 40, the friction is able to counter that and the object remains in equilibrium. The object remains in equilibrium. In this second case, we are applying a force of 40 Newton and the friction is able to counter that as well because the maximum possible value of friction is 40. So the friction in this case is also 40 and it is able to counter the force that we apply. However, there's a difference between these two situations. And the difference is, even though they're both equilibrium, the first one is equilibrium, the second one is equilibrium, both of these are equilibrium positions because the opposite forces are equal. The difference is, in case of 40 Newton, the equilibrium is actually at its limit. That if you were to increase this 40 Newton force by even a small amount, even if you were to make it 40.1 or 40.01, since the friction is going to stay at 40 Newton, the object will start moving. So this is kind of an extreme case of equilibrium that it has reached its limit. Even if you were to apply slightly more force than this, the object will start moving now. So equilibrium has kind of reached its limit at this point. This case is known as limiting equilibrium. Limiting equilibrium. When the force that you're applying is equal to the maximum value of friction, so friction has reached its maximum value now, you can't increase friction anymore. So if you were to apply a bit more force in this direction, the object will start moving. It's the limit of equilibrium. We call this limiting equilibrium. And if the force that you were applying was less than 40, this we can call non-limiting equilibrium then. That we still have room to increase this force and the object will still not start moving. For example, if you were to increase 15 to 16 or 17 or 30, 35, the object will still not start moving. It will only start moving if you increase it to above 40. Okay. So this case is called non-limiting equilibrium. All right. And then what about the top case? In this case, the force that we're applying is actually greater than 40. So in this case, the object starts moving. So in this case, we say the object is in motion. Okay. The object is in motion in this case. So there are three different cases that we have here. The object could either be in limiting equilibrium, or it could be in non-limiting equilibrium, or it could be in motion, as in it has started moving already. Now, in each of these three different cases, we need to understand what the friction value is, because we need to use that very, very frequently. One case is when the object is in non-limiting equilibrium. Let's start with that. So one possibility is that the object is in non-limiting equilibrium. Non-limiting equilibrium. When the object is in non-limiting equilibrium, you see, the friction value is still less than its maximum value. 15 is less than 40. Friction has not reached its maximum value yet. It's less than the maximum value. In case of non-limiting equilibrium, your friction is less than the maximum value of friction. In case of limiting equilibrium, you can see when the when the equilibrium reaches its limit, the friction is the same as the maximum value of friction. So when you have limiting equilibrium, F equals F max. And finally, when the object is in motion, what about that case? Now, you might be tempted at first, looking at the pattern, to write it as F greater than F max, but that does not make sense. Friction cannot be greater than F max, right? You see what's happening? Friction stop at its maximum value. It can't go any further. So when the object is in motion, in that case as well, friction is equal to F max. Okay. Now, what is F max? F max is mu into R. So in the first case, we can say friction is less than mu R. In the second case, we can say friction is equal to mu R. And in the third case, we can say, again, friction is equal to mu R. So when the object is in limiting equilibrium and when the object is in motion, in both of these cases, F equals mu R. Friction is at its maximum value. Friction is at its maximum value in case of limiting equilibrium and in case of motion. However, when it's non-limiting equilibrium, in that case, friction is less than the maximum value. F is less than mu R. Now, the first two cases that you have here, both of these cases are cases of equilibrium, right? This is also equilibrium. This is also equilibrium. So if you had a situation in which you just knew that you have equilibrium without knowing whether that equilibrium is limiting or not limiting, what can you say about friction in that case? You can say friction is either going to be less than mu R or going to be equal to mu R. So we'll say this is less than or equal to mu R. So when you just have equilibrium without knowing whether it's limiting equilibrium or non-limiting equilibrium, then you can say friction is either less than mu R or it's greater than mu R. It's one of those two cases. Is that okay? So these are the different cases that we have in this case. Now, the one in which you have limiting equilibrium or when you have motion. These two cases are used a lot. F equals mu r, F equals mu r in both of these cases. So you need to remember F equals mu r in limiting equilibrium and in motion. This one is not used as often, F less than mu r. However, this one is used, the one that has F less than or equal to mu r. This is also an important case. When you just have equilibrium, you will sometimes have to use F less than or equal to mu r. It's often when you are asked to prove some inequalities. I'm going to write this down here. We will refer to this later when we will do such problems. You will often need to use this case when you have to prove or find some inequalities. This is often used to find inequalities involving the coefficient of friction, which is mu. Okay. Yeah, I'm sorry, just give me a minute. My other device has an issue. Just take a minute. Okay, so these are the different cases that we have then. Let me summarize this now, the ones that you are going to be that you are going to be using more frequently. Okay, so let me just summarize this now. There are going to be two cases that you will be using more frequently. One case is when F equals mu r. When does that happen? When you have limiting equilibrium. That is one case. And also when the object is in motion. And then you also use F less than or equal to mu r. When you use that, you sometimes use this to prove inequalities involving mu. And when do you have to use it? When you just have equilibrium given without specifying whether it's limiting equilibrium or non-limiting equilibrium. So keep these two cases in mind. F is going to be equal to mu r only when you have limiting equilibrium or the object is in motion. And F is going to be less than or equal to mu r when the object is in equilibrium, when we do not know whether the equilibrium is limiting or non-limiting. Okay. So when we're doing questions, I'll often be reminding you about this again and again, that whenever you have limiting equilibrium written there, that should remind you of this directly. That's F equals mu r. Okay. So as soon as you read the phrase limiting equilibrium, that should remind you of F equals mu r right away. You're going to write that on the side, F equals mu r. Okay. Now, when we're doing questions, we will probably have a look at one before we end today. You will see that they will sometimes tell you that a situation is that an object is in limiting equilibrium. So they will sometimes use this phrase exactly as it is, that the object is in limiting equilibrium or the equilibrium is limiting. Sometimes they use some other ways to describe this same thing as well. Now, since it's kind of repeated pretty often, I'm just going to write those phrases here. There's some other keywords that they use to describe limiting equilibrium. So they might say the object is just about to, or on the point of slipping, sliding, moving. So the object is just about to move. Actually, write it as two different things. It's on the point of slipping, or on the point of sliding, on the point of moving, or it could say it's just about to slip or slide or move. So they often use keywords like this that hint towards limiting equilibrium. So whenever they say something like this, the object is just about to slip or just about to slide, just about to move, on the point of slipping, and so on, that also refers to limiting equilibrium. And whenever you have limiting equilibrium, that should quickly remind you of F equals mu r. Okay. So that's all that you need to know about friction. The maximum value of friction. So we understood the concept of friction. First of all, it's a type of contact force that applies parallel to the surface. It opposes the motion of an object. Then there's a maximum value of friction that's given by mu r. F max is equal to mu times r. There are three different cases that you can have. The object can either be in non-limiting equilibrium, or in limiting equilibrium, or in motion. And the first, F is less than mu r. And the second and third cases, it's equal to mu r. And when you are sometimes given the object is in equilibrium without specifying which equilibrium it is, you say F is less than or equal to mu r. And then these are some key phrases that you need to know about that they refer to limiting equilibrium. Okay. Now, before we end, let's have a look at one quick question from the friction worksheet. You will be attempting questions from this worksheet for the next class. Now, we will be spending the next two classes only doing practice questions from this worksheet now. Okay. There are a number of things that we want to discuss from those questions now. But it's really important that you attempt them first so that you know where you're having problems, and we can discuss them in class then. So let's start with a very simple and straightforward problem from this worksheet, and then we end today's class. So this is the worksheet that's uploaded on the classroom as well. Have a look at that. Have a look at the assigned questions. Or maybe it's not uploaded yet. I'll upload it today if it's not uploaded yet. I'm just doing question number 1 from this worksheet quickly before we end. Okay, question number 1. It says, a ring of mass 1.1 kg is threaded on a fixed, rough, vertical rod. Now, all the questions that we have done before this point, we used to have smooth surfaces. When you have a smooth surface, that means it does not have friction. Okay. Now, that's practically not the case in generally, because you don't have perfectly smooth surfaces. There's going to be at least some friction, but theoretically, we say the friction is so small, it's negligible, that you can just ignore that. Okay. Sorry. Now, it's a rough horizontal rod. A ring of mass 1.1 kg is threaded to this rod. It says a light string is attached to the ring, and the string is pulled with a force of magnitude 13 Newton at an angle alpha below the horizontal. You can see that in the diagram, where tan alpha equals 5/12. The ring is in equilibrium. If the ring is in equilibrium, that means the opposite forces are going to be equal. The force towards the left side is going to be equal to the force acting towards the right. The upward force is going to be equal to the force acting downwards. In the first part, it says, find the frictional component of the contact force on the ring. Contact force, again, friction is a type of contact force. They're just asking you to find the value of friction in the first part. Now, the first thing we do is we represent all the forces acting on the object. So what forces do we have acting on this ring? We have the weight of the object. 1.1 kg is the mass. Weight is going to be 1.1 times 10. That's 11 Newton. 11 Newton is the weight of the object. And so think about all those forces that you have to think about, right? That are not generally given in the questions: weight, normal reaction, tension, friction. Okay, so you have to think about all those forces in every question involving forces, that whether they are applying or not. Weight, we have represented that, that's 11 Newton. What about normal reaction? It's a surface. Rod is a surface, right? Normal reaction is going to apply perpendicular to the surface. Now the force is applying downwards, and there's a component of 13 Newton that's also going to act in the downward direction. Reaction is going to oppose these forces, so it's going to apply in the upwards direction. That's the direction of reaction. Okay, then we have tension. Well, we already have tension represented here. It's a string. It's threaded basically. The ring is threaded to this string, and the tension in that string is 13 Newton. So it's already represented there. What else? Friction. Where is the friction going to act? In what direction is the friction going to act? Any idea about that? What is going to be the direction of friction? Remember, friction acts parallel to the surface. So there are two possibilities. It could either be towards the right side or the left side. These are the only two possibilities. Now, since this 13 Newton force has a component towards the left side, the ring is going to try to move towards the left side. Friction is going to oppose that. So friction is going to act to the right. Okay, these are all the forces that we have. Now we just resolve these forces. What are the components of 13 Newton? There's one component of 13 Newton that's going to act in this direction towards left. One component is going to act vertically downwards. The component that's adjacent to the angle, that's going to have cos alpha. So this is 13 cos alpha. The component on the other side of the angle, that is going to be 13 sine alpha. So these are all the forces that we have. Now all we have to do is just equate the opposite forces. These are the forces acting horizontally, and these are the forces acting vertically. We just have to equate these forces. Okay, in the first part, they ask you to find friction. Where is friction? Friction is a horizontal force here. So all you have to do is just equate the forces acting towards the left side to the forces acting towards the right side. Towards the left side, we have 13 cos alpha. And towards the right side, we have F. Now, what is cos alpha? They have given us tan alpha. One idea is that you find the value of alpha using tan inverse of 5/12, and then put that value of alpha inside cos here, and then evaluate that. That is possible. But there's another method as well, which you should also know, because sometimes they ask you to find exact answers. In that case, it would not be a good idea to find the value of alpha here, because that value will be in decimals. We would not be able to write cos alpha and sine alpha in exact form. So how do you find them in exact form? Using something, you do that using something that you've done in P1 trigonometry. If tan of alpha equals 5/12, how is tan defined? Tan is perpendicular over base. We can say if perpendicular is 5, base is 12, then what about the hypotenuse? Hypotenuse is going to be square root of 5 squared plus 12 squared. That gives us 13. So hypotenuse is 13. If hypotenuse is 13, we can write the value of sine alpha and cos alpha now, because sine alpha is perpendicular over hypotenuse. Perpendicular is 5, hypotenuse is 13, so it becomes 5/13. And then what about cos alpha? Cos alpha is base over hypotenuse. That will be 12/13. You can just use these values here. Cos alpha is 12/13, and the value of friction therefore turns out to be 12 Newton, right? Friction equals 12 Newton. That's all that you had to do in the first part. It was equilibrium, just equated the opposite forces. And then part 2. In part 2, it says find the normal component of the contact force. What does that mean? Normal reaction. Normal reaction is also a type of contact force. You have to find the value of normal reaction. What do you do for that? You say upward force should equal the downward force. what's the upward force? The upward force is R. The downward forces are 11 and 13 sine alpha. So we say R should equal 11 plus 13 sine alpha. Okay, and what do we get from this now? R equals 11 plus 13 into sine of alpha. Sine alpha is, what is that? Sine alpha is 5 over 13. And that gives us the value of reaction, which is 11 plus 5, that's 16 Newton. That's R. That's the normal reaction. Okay. I hope that makes sense. So in the first part, we found friction, and the second part, we found the normal reaction. Now, let me have a look at a question that Joseph has asked. Yes, Joseph, as I said, you could do that. You could find the value of alpha from here by using tan inverse, and then put that value of alpha here. That is possible. I'm just saying, in this case, it's possible in this question because they do not require you to give exact answers. However, you will find problems where you have to sometimes prove inequalities, or maybe sometimes they ask you for an exact answer in terms of square root, for instance. In that case, you need to be using this method. So you need to be familiar with this method. In this question, it's not required to have an exact answer. So you could use tan inverse, but you have to know this method as well. Okay, this method is important. Part 3. Now it says, given that the equilibrium of the ring is limited, find the coefficient of friction, that means mu, between the ring and the rod. Now in the third part, it says the equilibrium is limiting. So now it's limiting equilibrium. Now, if it's limiting equilibrium, what that means is F equals mu times R. Okay. F equals mu times R. We already have the value of friction, that's 12. We already have R as well, that's 16. We can find the value of mu from this, 12 over 16. That's going to give you 0.75. That's the coefficient of friction that we were looking for. Okay. So it was a very simple example on limiting equilibrium and friction. I hope that makes sense. In the next class now, you will attempt, for the next class, you will attempt the assigned questions from the worksheet. At least try 7, 8 of them. And then we will be discussing those the problems that you have in the next class. The next 2 classes at least are going to be spent on this concept, okay? Because you will find that the questions are not that straightforward. So we will be discussing some of those questions in class, but that's for the next class. Any questions before we end? Any problems? Okay, let me have a look at this. Okay, Jazit, for question number 26, all you have to do is, okay, so Maheen or Rizal, can one of you please post in the P1 group that we will be starting in about 5 minutes?
Sure, sir.
Thank you. Okay, so Jazib is asking about this question number 26. I'll just give you a hint about this. So it says the weight is 21 Newton, and the particle P hangs in equilibrium 0.2 meters below the level of AB with both strings taut. You need to find the tensions in S1 and S2. All the rest of the information is mentioned in the question as well. Okay, so if you look at point P, You have three different forces acting. There's one force acting in this direction. It's called this T1. There's another force acting in this direction. It's called that T2. And then there is weight of the object. That's 21 Newton. Now there are three forces, and these three forces are in equilibrium. One idea is to use Lami's theorem. That will make it very quick. If you can find the angles between the forces, this angle, and this angle, you can use Lami's theorem to find S1 and S2. Or you could resolve the forces, find the component of T2 in this direction and this direction, find the component of T1 in this direction and this direction, and then equate the opposite forces. You'll have simultaneous equations. You can find T1 and T2 from that. But in order to use any of those two methods, Lami's theorem or resolving forces, the first thing you have to do is you have to find the angles. Only then you can use one of those two methods. How do you find the angles? The whole purpose of giving you these lengths is that you're able to find angles using those lengths. How would you do that? You can make these right angle triangles. You can find this angle. Let's call this theta. Theta can be found like this. Cos theta equals 0.2 over 0.52. And similarly, you can find the other angle. Let's call this theta 1 and the other one theta 2. What about theta 2? Cos theta 2 would be 0.2 over 0.25. You can find the value of theta 1 and theta 2 from this. And then you can use any of those two methods, either Lami's theorem or resolving forces. If you have to resolve forces, this would be T2 sine theta 2. And the upwards force will be T2 cos theta 2. And for T1, you would have T1 cos theta 1 here. And on this side, you would have T1 sine theta 1. Just equate the opposite forces. You have two equations, solve them simultaneously, and you should be able to find the values of T1 and T2. Or use Lami's theorem. That will be even quicker in 2 steps. You can do that as well. Will you be able to do that? Do it now? Yeah, okay. Okay, all right, great. Okay, so that's it for today. I'll see you again in the next class. Allah Hafiz. Please make sure that you do those practice questions. That's important, because then when we discuss those questions in class, it'll make things a lot more clear for you, as opposed to me doing everything for you and then you might not really understand it that well if you haven't attempted those questions before yourself. Okay, all right. I'll see you again in the next class. Allah Hafiz.